Hello. Well, thanks to everybody who's commented on my previous video, what shall I do with this Harrison M300 lathe? The comments, very few people were in favour of buying the Taiwanese lathe. The comments seem to divide fairly evenly between people who say, well, you've come so far, push on, get the beds reground and then you'll have a good lathe. And people who say, you'll never be happy with it, splash out for a new Harrison M300 and enjoy it. And I still haven't decided what to do, but I've been slightly put off the idea of pushing on with this lathe because of the problems I've had with threading, which I described in the video before last. And this video is an update on that. To recap, what we were doing was cutting an M10 1.25mm pitch thread using a full profile insert in mild steel. Second spring pass coming up. That's fine up to there, where it starts getting seriously stiff. Now what I'm going to do is take this much off the thread and then see if this thing will go on further. It's got to go on, hasn't it? Yes. Yes, well that will now go right on, which does suggest that it's a pitch mismatch problem. So in an attempt to confirm that the lathe was in fact cutting the wrong pitch, I left the lead screw engaged and turned the spindle by hand and measured the distance that the saddle travelled towards the chuck, and thus produced this graph. Well, those measurements came out on a remarkably straight line. Every single point is slap bang on a straight line, which is most unusual for my measurements. And the slope of the line, as determined by Excel's linear regression, is 1.2474 millimeters, which is not 1.25. So we have proved that at a pitch of 1.25 millimeters, the gearbox cannot quite produce the correct figure. Well, in fact, that conclusion was wrong, as we'll see later on in this video. But I think looking at the comments, some people may have been sceptical as to the accuracy of this measurement, which is rather crudely taken with a metal tape measure and the Mark I eyeball. However, I would disagree with that. I think it is satisfactorily accurate because I think I can measure a point on the tape measure to plus or minus 0.1 millimeters. In other words, if the true measurement is 97.3, say, then I might measure it as 97.3 or 97.4 or 97.2, but I'd be unlikely to measure it as 97.1 or 97.5. So if we accept that as a reasonable estimate of the accuracy of my measurements, then the error in the slope of this line is, because it's measured over 324 millimeters, it's plus or minus 0.2 millimeters over 324 millimeters, and that is 0.06% error. Whereas the difference in slope that we're trying to measure, the difference between 1.2474 and 1.25, that is 0.2%. So the errors in the measurement are an order of magnitude less than the errors that we're trying to measure. So I think that's okay. But of course the linear regression that gives that slope of 1.2474 is utilising all the points over the whole distance of 324 millimetres. But it gives us an average slope. It doesn't tell us if there are large variations in the slope in particular places along the bed. Well, I thought that the measurements I made with this tape measure, although it's crude, I thought they were reasonably accurate because I was measuring over such a long distance. But one of the people in the comments, Jonathan Crosley, suggested that I should measure using a clock gauge. So I've got a mark on the spindle here, and the half nuts are engaged. I can rotate the spindle, bring it back to the mark, take the reading, repeat. In that way I got a set of 8 readings corresponding to 8 revs of the spindle up here, and also the same thing only with the carriage much closer to the chuck. So those are the results of those measurements. Spindle revs from 0 to 8 and the reading on the dial indicator in millimetres. This one, the blue one, near to the chuck, this one, the orange one, halfway along the bed. You see that the two lines are almost exactly on top of each other, except the orange one is a slightly greater slope, and the Excel linear regression gives a figure of a pitch of 1.246 halfway along the bed. Notice that's just below 1.247, which we had when we measured it with the tape measure, presumably because further along, even further towards the tailstock, the pitch is bigger. And near the chuck, the pitch comes down to 1.225. So these measurements confirm what I'd already worked out with the tape measure. Then I thought, well, what we've got here is 8 spindle revs, and the reduction from the spindle to the lead screw is 4.8. So we've got, just under 2 revolutions of the lead screw in this. So I wondered if we just look at the pitch from one point to another, like for example here, I'm just subtracting these 2 figures to get the pitch from this point to that point. You can see that they do change quite a lot, and I plotted those down here. I think we can see that the pitch is changing much more close to the chuck, the blue one, than it is halfway along the bed. And the pitch halfway along the bed is pretty damn close to 1.25, what it should be. Slightly odd thing about both of these graphs is that the first point seems to be, out of line, depressed downwards. And that is so even though when I set this thing up, I wound the spindle 3 turns further than I wanted to go, and then wound it back 3 turns in order to remove all the backlash in the gearing. Or so I thought. Maybe with a reduction of 4.8, maybe I should have wound it back even further. So maybe we should treat these points with a suspicion. And then I got to thinking, well, I wonder how accurate these measurements are anyway. I had a look at the Mitutoyo 10mm dial indicator, and it says here maximum permissible error any one revolution 10 microns. Well, it's actually 1¼ revolutions between readings here, but let's just take this figure of 10 microns as the possible error in each measurement that I've made. What I've done here is put 10 micron error bars on all the blue points. As you can see, ignoring the left-hand point, the error bars would almost bring the blue line within range of the nominal pitch of 1.25. Now that's with a Mitutoyo indicator. The indicator I'm using is a no-brand one, which may be far less accurate. So I'm not sure that we're learning a great deal from this, but you can see that there's definitely, despite these error bars, which apply to both the orange and blue curves, the orange curve is much closer to 1.25 than the blue one. I was also thinking, well, the pitch error that we're trying to measure is 0.2% below 1.25 millimeters. As I'm turning the spindle by hand and bringing it back to a mark, 0.2% of 360 degrees is 0.7 of a degree. 7/10 of a degree, which is just slightly more than the smallest division on this protractor. So the question is, can I reliably rotate the spindle and bring it back to exactly the same position it was when I started? And I thought, no, I can't do that without some kind of physical stop. This is a slightly improved procedure whereby I've got a positive stop on here. So can rotate the spindle like this. Bring it back to here. Take the reading on that, which is 2.46, and so on. Another interesting thing is that it's hard to see how wear in the lead screw could actually affect the pitch. So when we're threading towards the chuck, the lead screw is pushing on the half nuts, which is pushing the saddle this way. So all the force is on the chuck side of these threads. And if the wear is uniform along the lead screw, that cannot have any effect on the pitch. At least that's my theory. I'd be very interested to know the theory of anybody else in the comments. All that will happen if we keep threading towards the chuck and wear this lead screw is that the left-hand side, or the chuck side, of each of these raised threads will get worn away and therefore make these threads narrower. That will increase the backlash between the lead screw and the half nuts, but that does not affect the pitch. So to get a change in pitch from wear in the lead screw, it's my theory that you actually have to have differential wear along the lead screw. And I was only turning something that was about that long. So there has to be differential wear within that distance in order to reduce the pitch. And I find that somewhat implausible. But this is what we're measuring. So how do you explain that? It seems very unlikely that any lathe would be used equally for threading towards the chuck and also for threading away from the chuck. So it's likely that the side of the lead screw that is facing the tailstock or away from the chuck would be a lot less worn than the side of the lead screw that is facing towards the chuck. So Jonathan Crossley suggested that I should measure also running the spindle backwards and pushing the carriage away from the chuck using the lead screw, which I did here. that's the blue line you've already seen, which is exactly the same here. So the blue line is near to the chuck and threading towards the chuck, and the green line is near to the chuck but threading away from the chuck. And indeed we do find, ignoring this, the first point as usual, that the green line is somewhat closer to the 1.25 pitch ideal value than the blue line is, but not enormously so. By this time I was beginning to wonder whether wear in the lead screw could really account for the change in pitch that I thought I'd observed. So I began to wonder if I'd made some other horrendous error during the rebuilding of this lathe. So I counted the teeth on all these gears and verified that they were in fact correct, and that I hadn't got the wrong change gears in by mistake. I also wondered whether I'd made a horrendous cock-up in reassembling the feed gearbox, maybe got the gears back to front or something. I spent a considerable amount of time viewing the videos of the feed gearbox refurbishment with a view to finding out exactly what gears are engaged when I select a pitch of 1.25 millimeters using the knob settings BS3W, and the gears are those shown there in green. And if we do the calculation, the first two are the change gears at the back of the headstock, and then there's 19 into 19, which does nothing, 23 into 23, which does nothing, 20 into 22, which does something, 36 into 36, which does nothing. The overall result is exactly 1 over 4.80 reduction from spindle to lead screw. The lead screw pitch is nominally 6 millimeters. So that gives exactly a pitch of exactly 1.25 millimeters. So what I said at the end of the previous threading video and recapped at the beginning of this threading video, the assumption that I jumped to, that the M300 maybe, when set on a pitch of 1.25, could not accurately reproduce that pitch, that assumption was wrong. With the gearbox set up correctly, it does produce exactly 1.25 millimeters pitch. So the problem I'm observing is not caused by a reassembly cock-up. I've actually run out of 12 millimeter diameter steel rod, so I can't do any more test cuts. I just chewed it all up practicing threading. So when yesterday the postwoman delivered me this package, my first thought was that it would be some steel rod. But when I picked it up, I realised it couldn't possibly be. I had ordered some capacitors from Farnell because I'm recapping a Roberts radio which dates from 1978. And I thought, this actually says Farnell on it, so I'm thinking this is a really weird way to package capacitors. The only other thing I ordered from them was some heat shrink sleeving. Could this be heat shrink sleeving? I have to say that this is just about the weirdest package of electronics components that I've ever received. Slightly bent in the middle. Well, see if I can cut off the cap on this end. Come out, you rat! Oh. Well, that's one metre of sleeving. I expected a bit more than that. Is that it? Is that the sum total of everything? Well, what's this then?
ordered more than a metre of sleeving, surely for goodness sake. There's nothing here. That's all there is. A metre of sleeving. Well, it's better than nothing, but I thought I'd ordered considerably more than that. Well, anyway, when I get some more steel rod, I'm going to do another test threading using a long piece of rod so that I can thread up near the far end of the lathe bed, well away from the chuck, with a live centre and or a steady rest, and just see whether I have the same pitch problem there as I do near the chuck. So that'll be an interesting exercise. I might repeat the micrometer measurements, but winding the chuck 6 turns back from the place where I want to start, in order to be absolutely certain of removing backlash in the gears before I start measuring. Maybe that would get rid of that anomalous point on the left-hand side of those graphs. So that's where I am with this at the moment, and any comments gratefully received as to how we can explain this pitch mismatch. If it is a pitch mismatch. If it isn't, what is it? What's causing this problem of not being able to thread on a long nut? Okay, thank you very much for watching, and Happy New Year.